In section 3.7, we're going to look at a topic called related rates. Another important use of the chain rule is to find the rate of change of two or more variables that are changing with respect to time. For example, if we were to look at a scenario where we had water that's in a cone, and let's suppose there's like a hole in the bottom of the cone so that water is able to kind of drip out and pour out over time. If you look at the body of water that's in that cone, it's going to be a cone shaped. The cone is described by two values. So you need to know the height of the cone, and you need to know the radius of the cone, and that would tell you how much water that little sub-region or sub-portion of that cone would hold. Now, as the thing drips out, obviously the water level is going to go down, so not only will the height change, but the radius will also change as well. And so what that tells us is that the height and the radius are functions of time. You might recall from geometry, but the volume for the formula of a cone, the volume of a right cone is pi over 3 times r squared times h. Where we think of all of these variables, even though we're not writing it right now, we're thinking of them as all implicitly depending upon time. So r is a function of time, h is a function of time, etc. Because of this, we can take the time derivative of both sides. So let's take the derivative of the left-hand side with respect to time, the derivative of v with respect to t, we're going to call that dv dt, and now on the right-hand side, to take the derivative of pi over 3 r squared h, you can kind of keep the pi over 3 factored out, and it's going to be the derivative of r squared times h. This is a derivative with respect to time, and we know that both r and h are functions of time, so we're going to need to use the product rule on this. Okay. Furthermore, instead of using a prime notation, because it can be a little bit confusing, we have variables v, r, and h. We're going to use the Leibniz notation in order to specify specifically which derivative each variable is taken with respect to. We know to take, according to the product rule, the derivative of r squared, that would be 2r, but because r depends upon t, the chain rule would say multiplied by the derivative of r with respect to t, that's dr dt, leave the h alone, and then plus, now we would leave the r squared alone. The derivative of h would be 1 times the chain rule, the derivative of h with respect to t, we call that dh dt. And all things considered, we get our formula for the derivative of the volume with respect to time. It's pi over 3 times r squared dh dt plus 2hr times dr dt. Let's take a look at example 1. Both x and y are differentiable functions of time, or of t, we should say, and we know that y and x are related via the equation y equals x squared plus 3. We're asked to find dy dt when x equals to 1, given that dx dt is equal to 2 when x equals to 1. So this is a pretty typical related rates problem. What we're going to start off by doing is by taking the time derivative of both sides. So let's take the derivative of both sides of our equation with respect to t. The derivative of y with respect to t, we call that dy dt. This is equal to the derivative of x squared. Well, we know that that's 2x, but because x is a function of t, from the chain rule, we need to multiply by the derivative of x with respect to t. That's that quote-unquote derivative of the inside part, and that's dx dt. The derivative of the constant 3 would simply be 0. So step 1, take the derivative with respect to time of both sides, and now that we've done that, now we can go ahead and evaluate our derivative. We want to find dy dt. We know x is 1. We also know that dx dt is 2, so I can plug those in, and we would find that the rate of change of y with respect to time would be 4. So dy dt is equal to 4. Let's take a look at example 2. In example 2, they say that a pebble is dropped into a compound which causes a rippling effect that forms concentric circles. Okay. I think most of us have done this. You throw a stone in a body of water, and what you kind of see is you get these outward moving concentric circles. They would have some radius, let's call them r. Okay. So as time increases, so after we throw the stone, as we watch the passage of time, we see that the outermost circle gets larger and larger and larger. We want to know when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we need a formula for the area, and this is going to be the area of a circle. We know area of a circle is pi r squared. We can now take the time derivative of both sides. The derivative of area with respect to time, well, we call that dA dt, is equal to the derivative of pi r squared. Well, pi is a constant, so you can leave the constant alone. Derivative of r squared we know is 2r, but because r is a function of time, r changes when time changes. From the chain rule, we need to multiply by the derivative of the inside function. The derivative of r with respect to t, we call that dr dt. So we have that dA dt is equal to 2 pi r dr dt. Okay. So we wrote down our equation. We took the time derivative with respect to both sides, and now we can go ahead and plug it in. We are asked to find dA dt when r is 4 feet, so our r is 4. So let's go ahead and plug that in. And we are told that the radius of the outer ripple is increasing at a constant rate of 1 foot per second. That means that dr dt is 1, so we can plug that in, and this is going to give us 8 pi. It's a rate of change of area, because the units are measured in terms of feet. Area will be in feet squared, and time was measured in seconds. So the rate of change of the area is going to be 8 pi feet per second. If you wanted an approximation for this, that'd be about approximately 25.1 square feet per second. Okay. Especially important with these applied related rates questions to attached units. The numbers, are nice, but we also want to make sure we're giving a full answer. So make sure you attach units where appropriate. So the rate of change of the area with respect to time is feet squared per second. One of the things that I find oftentimes can kind of be helpful to get the units correct is if you just forget the differential for a moment. Area, we know that's square units. So that's where we get the feet squared. And we know time in this case is measured in seconds. So the units for the final problem should be feet squared per second squared. It's going to be units of area divided by units of time. Some of the guidelines that will kind of help us to solve these related rates questions, and these are good steps to always kind of follow. The first step is to identify all of the quantities and the quantities to be determined. So what information do we know? What kind of things are we trying to find? If it's a geometry-based question, or a question in which you can actually draw a rough sketch and label the quantities, that's oftentimes an excellent starting part. We then want to write an equation involving the variables whose rates of change are either given or are those that we're going to find. So we understand the situation, we go ahead and we write down an equation. The next thing we're going to do is, using the chain rule, we're going to implicitly differentiate both sides of the equation with respect to time, and then only after we've differentiated both sides and simplified do we go down to step 4, which is substituting in the known values and solving for our unknown. Let's take a look at example 3. They tell us that air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. 4.5 cubic feet per minute, that's discussing a change in the volume. So the rate of change of this volume with respect to time is 4.5 cubic feet per minute. And we're asked to find the rate of change of the radius when the radius is 2 feet. So we know we're going to use a radius of 2 feet, and we're looking for the rate of change of the radius. That would be represented by dr dt. If we want to, we can kind of draw a sphere. Just think of like a balloon at a kid's party. Here's what it looks like. Here's my radius r, and I'll put a string on the balloon. And as time increases, this balloon is inflating, it's getting blown up, so it's going to get a larger radius. First thing we want to do is write down an equation that relates our given information to the unknown. That's going to be the formula for the volume of a balloon, which is a sphere. The volume of a sphere is 4/3 pi r cubed. I can now take the time derivative of both sides. So we have 4/3 pi r cubed. On the left-hand side, the derivative of volume with respect to time, we call that dv dt. This is equal to, here, 4/3 times pi is just a constant. So leave the constant alone. It's the constant multiple rule. The derivative of r cubed is going to be 3r squared, but from the chain rule, because r depends upon time, the derivative of the inside function we would call dr dt. We can simplify this a little bit. You can cancel out the 3's, and we get that dv dt is equal to 4 pi r squared times dr dt. We're actually asked to solve for dr dt. You can do that by dividing both sides by 4 pi r squared, and I'm going to write it as 1 over 4 pi r squared times dv dt. So we found our derivative, we simplified for the thing we're looking for, and now we can go ahead and plug in. They say we want to find this when the radius is 2. So everywhere I see r, we can plug in 2. And we recall that dv dt was 4.5. We would get that dr dt is equal to 4.5 divided by, in the denominator, you're going to have 2 squared is 4. 4 times 4 is 16. So this would be 16 pi. And if you didn't want to have like an improper fraction or something goofy with the 4.5 up top, you can multiply top and bottom by 2, and that would give us 9 over 32 pi. This would be the exact answer, and this would be in terms of feet per second. Excuse me, feet per minute. The volume was given in terms of feet cubed, so the radius must have been in feet, and the time was in minutes. So it's going to be 9 divided by 32 pi. If you want an approximation for this, we can give that as well. We would get the following. So dr dt, it's going to be approximately equal to 0.09 feet per minute. So this would be the exact answer. This would be the approximate.